Have you ever wondered what the surface of the sun looks like up close and personal? Well, get ready to have your mind blown, because the latest video from NASA is like nothing you've ever seen before. Step inside the world of the sun and witness its fiery, magnetic storms as they rage across its surface. Get up close and personal with the sun's stunningly intricate sunspots, and watch as they twist and turn in a mesmerizing dance of energy. So buckle up and prepare to be transported on an interstellar journey to the heart of our solar system, where the secrets of the sun's surface are waiting to be uncovered. What is the sun made of? The sun is a huge ball of hydrogen and helium, held together by its gravity. The sun has several regions. The interior regions include the core, the radiative zone, and the convection zone. Moving outward, the visible surface or photosphere is next. Then the chromosphere, followed by the transition zone, and then the corona, the sun's expansive outer atmosphere. Once material leaves the corona at supersonic speeds, it becomes the solar wind, which forms a huge magnetic bubble around the sun, called the heliosphere. The heliosphere extends beyond the orbit of the planets in our solar system. Thus, Earth exists inside the sun's atmosphere. Outside the heliosphere is interstellar space. Ion. In the sun's core, gravitational forces create tremendous pressure and temperatures. The temperature of the sun in this layer is about 27 million degrees Fahrenheit, 15 million degrees Celsius. Hydrogen atoms are compressed and fuse, creating helium. This process is called nuclear fusion. As the gases heat up, atoms break apart into charged particles, turning the gas into plasma. The energy, mostly in the form of gamma-ray photons and neutrinos, is carried into the radiative zone. Photons can bounce around at random in this zone from somewhere between a few thousand to about 1,000,000 years before traveling to the surface. Radiative zone. The radiative zone is the thickest layer of the sun at 0.45 solar radii. From the core out to about 0.7 solar radii, thermal radiation is the primary means of energy transfer. The temperature drops from approximately 7 million to 2 million Kelvin, with increasing distance from the core. This temperature gradient is less than the value of the adiabatic lapse rate and hence cannot drive convection, which explains why the transfer of energy through this zone is by radiation instead of thermal convection. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold, from 20 grams/Tm3 to 0.2 grams/Tm3, between 0.25 solar radii and 0.7 radii, the top of the radiative zone. Tachocline. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and the differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. Presently, it is hypothesized, see solar dynamo, that a magnetic dynamo within this layer generates the sun's magnetic field. After core hydrogen exhaustion, the sun does not have enough mass to explode as a supernova. Instead, when it runs out of hydrogen in the core in approximately 5 billion years, core hydrogen fusion will stop, and there will be nothing to prevent the core from contracting. The release of gravitational potential energy will cause the luminosity of the sun to increase, ending the main sequence phase and leading the sun to expand over the next billion years, first into a subgiant and then into a red giant. The heating due to gravitational contraction will also lead to hydrogen fusion in a shell just outside the core, where unfused hydrogen remains, contributing to the increased luminosity, which will eventually reach more than 1,000 times its present luminosity. When the sun enters its red giant branch, RGB phase, it will engulf Mercury and, likely, Venus, reaching about 0.75 AU, 110 million Chem, 70 million Mi. The sun will spend around 1 billion years in the RGB and lose around a third of its mass. The surface of the sun. The surface of the sun is called the photosphere, a term which means sphere of light. The glowing ball of light that you see in the sky is the photosphere. The surface of the sun is the only part that we can see from Earth on a typical day, without the use of specialized equipment. The photosphere is cooler than the layers around it. The photosphere is a thinner, cooler layer than its neighboring layers. It is only about 500 kilometers, 300 miles, wide, a much thinner layer than the interior solar regions. The temperature of the photosphere is around 5,500 degrees Celsius, 9,900 degrees Fahrenheit, which is much cooler than the sun's core. Most of the light energy produced in the sun's core escapes from the photosphere. Because the plasma is cooler and less dense at the surface, there are fewer collisions to trap the energy-carrying photons within the sun. Instead, energy radiates away through space, some of it reaching Earth. Surprisingly, the photosphere is also much cooler than the atmosphere above it, which has regions with temperatures as hot as 2 million degrees, 3.5 million degrees. There is some variation in temperature from place to place within the photosphere. For example, sunspots are relatively cool regions with temperatures as low as 3,000 degrees Celsius, 5,400 degrees Fahrenheit. What's on the surface of the sun? Sunspots, indicators of disturbed magnetic fields, are the most common features seen in the photosphere. Sunspots are generally surrounded by lighter areas called faculae. Observing sunspots drift across the surface helped astronomers discover that the sun rotates on its axis. The polar regions take longer to complete a rotation than the equatorial regions because the sun isn't solid. Close-up views of the photosphere also show patterns of light areas surrounded by darker borders, called granulation, similar to the patterns you could see at the top of a pot of boiling water. Granulation is caused by heat rising to the photosphere from the hotter solar interior. Where the hot rising blobs of plasma reach the surface, we see bright areas. The darker boundaries of the granulation cells are places where the plasma has cooled and is sinking back into the sun's interior. The active regions around sunspots often cause solar flares, which are explosions of radiation that extend hundreds of thousands of miles above the sun's surface, producing bursts of X-rays, ultraviolet radiation, and radio waves. Solar flares are just one example of how activity on the surface of the sun can affect the entire solar system, including Earth. In conclusion, exploring the surface of the sun is a fascinating and awe-inspiring journey that reminds us of the incredible power and beauty of the universe. Thanks to the advanced technology and tireless efforts of scientists and researchers, we can now witness firsthand the magnificent and complex patterns that exist on the sun's surface. From the swirling plasma to the fiery solar flares, the sun is a dynamic and ever-changing celestial body that continues to captivate us. If you found this video informative, make sure to hit the like button, share it with your friends and family, and subscribe to our channel for more exciting content like